There we go. Okay. So I should have the exams back to you guys. I mean, I should finish the exam grading today, and then what I'll do is I'll post the grades online um, by like maybe the last four digits of your banner ID number. I could do it that way. And then in class on Wednesday, I'll hand the exams back. Okay. Yeah. Does anyone object having their, because like maybe some people are identifiable with their last four digits of um, their banner ID? Does anyone object to that? Um, I just don't know how to do it on Canvas that way. But I have an Excel spreadsheet, and then I could just do like your last four digits, and then post that. But yeah, I got to find out how to do that on Canvas. So.
That'll just be the grade.
Yeah. Well, yeah, the score. Yeah, the score. Yeah, exactly. Um, or if you don't want that, then you could just wait until Wednesday when you get the actual physical exam back. Huh? Spreadsheet? Okay. All right, then. Okay, so we're on 16. So for a quick review, we lecture 14, we looked at cascade macro modeling, where we abstracted the amplifiers into these macro models right here, modeled as these input resistances, output resistances, and these voltage controlled voltage sources. And here's the gain of the whole thing right here. Here's the input, here's the output, and these are the gains it goes through. Now, if these outputs are really small, then you can eliminate this part right here, and then this becomes 1, and then you get this right here. So this is a good estimation if you have a very small output resistance, as seen at the output. We also looked at a low-pass filter, which is like this, where this part is a low pass, these frequencies get through. If you have a high Q, it'll peak right here before the cutoff starts going down like that. But this is the one you want right here, this path, typically. And also, by chaining all these together, you get higher and higher orders, right? So just the first one is 20 decibels per decade. Having 2, you get 40. 3, you have 60 decibels per decade. And so this increasing order as you fall off right here. And that only changes slightly the cutoff frequency. But basically, you have the cutoff frequency. Here's a brick wall ideal. That's what you're trying to get to, but of course, it's hard to get there. We also look at an instrument amplifier. And then on lecture 15, we looked at low pass, high pass, band pass, all three of those. And we looked at the characteristic equations of each one of those right here. And we saw how the amplitude, the transfer function is related to the frequency and the quality factor. Here's the cutoff frequency. Here's the quality factor in terms of capacitors and the resistors in each one of those. We're here and also here. We also looked at the magnitude scaling and frequency scaling. So for magnitude scaling, we found out that if you just want to scale the magnitude and leave the cutoff frequency alone and quality factor alone, then you have to change each resistor by a factor km and divide each capacitor by a factor km. If you do that, only the magnitude will increase by a factor km, but the cutoff frequency and the quality will remain the same. For frequency scaling, what you want to do is scale the frequency, so the frequency will scale by some factor kf, but the quality will be left alone, the quality factor. And what you do here is leave the resistors alone, but you divide the capacitors by kf. And then we also got into switch capacitors, so we'll do more of this today. Okay, so for today, we'll finish this section on switch capacitor circuits and then go into digital analog conversion. And then next lecture we'll do analog to digital. Okay, so here's where we left off, where we saw that we could take this integrator circuit. Why do I have this here? okay, we take this integrator circuit right here and replace this resistor by these switch capacitors. That's the idea of having these switch capacitors. And the reason for doing that is because for integrated circuits, to get like a really high resistance, this takes up a lot of chip real estate space. And since these can be made really small and you can get really high resistances this way, then that's the way to go. There's also other benefits too, but that's a major one right there. Okay, so the idea is for these switches, S1 and S2, they have these phases where you apply a voltage here, and that closes the gate, and then current is able to pass through. And if that's open, then current can't pass through. So these are switches that you can open and close. So if phi1, if that phase, if it's high, then this is closed, current goes through, but at the same time, this phi2 is closed. Okay, and so so these are happening, simultaneously. So when that's high, that's low, or if that's closed, that's open. And then when that's closed, then that one's open. And there's like a little offset right here. So the switching doesn't happen exactly the same time. So what could happen is that the charge can transfer from one to the other, or is allowed to pass through from like this capacitor over this capacitor. So this is what happens on phase 1. So on phase 1, this switch right here is closed. So and this one's open, right? So this open circuit right here. So that's this situation where this is just closed. This switch is open, so it looks like that. So all you have is this going to ground right here, and this piece is going up to that right there. So once this is closed, then the voltage across here becomes the voltage across here, and positive charge is able to accumulate here. Negative charge, the same amount, is on this end. So that's phase 1. And then it switches where this becomes open, and this one over here is closed, and you have this situation right here. And then what happens is that the charges that have accumulated over here will move up to this capacitor. This is at ground, so that's going to be at ground. This over here is can change, right? So this side is like 0 volts, and that one right there is going to be some change in voltage.
How
So,
quickly are these switches switching, like, to make this happen?
well, the nice thing about it is controllable, because as you'll see, because you can control the frequency of the switching, that means you can also control the resistance.
Yeah, but like
Yeah.
order of magnitude, like I'm trying to like imagine like how quickly this needs to be happening.
Oh, they can happen like thousands of times per second. Yeah, it's happening really fast. Yeah. Otherwise, it's like a very discrete sample. But if it's happening really fast, it's not quite continuous. But for many systems, it can be thought of as being continuous. But there is like a limit on your sampling frequency that you want to try to maintain. So so what's happening here is that the charge that's built up on this capacitor right here, once that closes, it goes over here, and here's the positive sense of current flow. And so one way to understand that is like this. So so let's say you have your capacitor right here, and then let's say this is okay. So on phase 1, what happens is that positive charge will accumulate over here. Wait a minute. Let me do the right orientation. So positive charge will accumulate over here, and the same amount of negative charge will be on this side. Okay, and it'll be at some voltage V1 across here. Okay, so that's what that amount is right there. So that's your Q1. And then once that switch opens, you have your charge here, then that switch closes, and so what happens is you have your capacitor over here. Now, this capacitor, it does have like a delta Q and a delta V over here, because there may be some charge over here depending on what that voltage used to be at some prior time, right? So there could be some charge there. You know, for example, let's say, I don't know, let's say it has this much charge there, right? And so when the switch is closed, and when this one opens and this closes, what happens is that for each charge that leaves here and goes over there, you could think of it as these two charges coming together like that. And so now you just have two negative charges, and this charge is now able to leave in that direction. Because if you have just two negative charges, then you can match it up with two other positive charges on the outside. This will leave. So that's like the kind of current flow. And remember, this over here is constrained by being grounded, because it's like the op amp right here. And so what's happening is, if you have a capacitor and you have charge coming off that capacitor, it's basically discharging, right? And so the voltage that you're picking off right here, this V out, is actually going downhill. It's changing downhill from a high value to a lower value. Like the voltage across here is decreasing in time, right? Because each charge that's leaving is decreasing in time. Eventually, because, was it showing that? Yeah, so eventually, since this piece since the upper side is grounded and that's grounded, they have the same potential, then eventually you won't have any charge stored in that capacitor. All the charge will have dissipated off. But that's the direction of current flow. And because of that, the voltage is decreasing in time for each amount of charge that's, each time that switch is closing, more and more small amount of charge is going onto this capacitor, and more positive charge is like leaving in time, and the voltage is decreasing. And anyways, so this negative sign right here, this is also negative, right? It's changing, decreasing in time, right? So this right here is positive, but really you have two negatives on that side over there. Okay, so another way to think about this is this right here. So this charge Q1 that accumulated right here, it has this current over this amount of time, and that current can be thought of as this voltage V over R, right? And also Q can be thought of as CV. Okay, so solving for R, you could think of it as T over C, and that sort of makes sense, right? Because we already know the relationship between time and ohms and farads, right? So we already know that time constant, tau, which is in seconds, is the same thing as ohms and farads. So ohms and farads is seconds, right? So unit-wise, this makes sense. And this period, your sampling period right here, can just be thought of as 1 over your sampling frequency, 1 over the frequency FC. So that's the clock frequency, and that means that you can control the value of R by controlling your sampling frequency of your clock. And here's an example we went over where you have like maybe that's 1 picofarad for your capacitor, right? And your switching frequency is 100,000 hertz. Then what your resistance is, it looks like a 10 mega ohm resistor. Okay, and that's like one of the great things we were just talking about, that this value of resistance for integrated circuits to be like really small, you can get a really large resistance in a very small amount of area by using switch capacitors. So what happens at every clock cycle is this. So here's like, continuous time or discrete time. And so at that nth time is n times your period, right? So your voltage at your output right here, that voltage, this is what happens at that particular time, some n period time later. It's the voltage that it used to be right here at, well, that's nt. Here's n minus 1 times t. So that's like 1 period earlier. So it's what the voltage it used to be minus your new voltage. So this is the voltage that's coming from V1, which is right here. Oops. So it's this right here. And so is this last voltage minus this piece right here. And that's why this is going downhill, like decreasing in time. Yeah, so this is what is what's happening. The relationship between V out and Vn right here. And it looks just like an inverting amplifier, right? Where instead of having negative RF over Rn, you have negative C1 over C2. And here's the feedback capacitor on the bottom this time. But it's still like this ratio. It's negative. Okay. All right, so let's look at non-inverting switch capacitors for integrators. So the polarity can be inverted without even using an inverting amplifier. And so let's go over that kind of scenario. So in this scenario right here, you have 4 switches, and you have this floating capacitor right here. Okay, so you see this is S1, that's S1. Here's S2, and that's S2. So these two guys are, and they both have this Phi1 and Phi1, Phi2, Phi2. So these two guys are going to open and close at the same time, followed by these two closing and opening like that. Okay. So for this non-inverting integrator, here's what happens. So when S1 is closed, that's closed, and also this is closed. Okay, so it looks like this path right here. It goes through here, the S1. It doesn't go down this way because remember, this is open, so this is an open circuit. So ignore that. So here's a capacitor right here, C1, and then it goes down this direction straight to ground. Okay. This path right here. Oh, and I don't want to confuse you guys. These are not arrows. These are the switches, okay? So this is not the current direction. So what's happening on this situation is you're applying voltage. Positive charge Q accumulates on this side. The same amount of negative charge is on this side, right? And this part is disconnected. So, but it's just holding whatever that is right there. Then on the next part of the cycle, then the S1's open, right? And the S2's close. So that's going to close, and that's going to close. And so what's happening is, these two are now closed right here. And now you have this situation where you have this positive charge on this side, and now this positive charge now goes in this direction off that way. And because the positive charge is leaving off, right, then you have another negative charge that's not, where you're going to have another positive charge that comes from here that's going to come over here and knock off that negative or, eliminate it. Right? Because remember, you have to have the same number of positive and negative charges on both sides of your capacitor. Okay, so in effect, you have current flow going this direction. Okay, so remember in the last one, we had current flow going this direction. Okay, now we have current flow, oops. Sorry. So now we have current flow going this direction. Okay. So that's one thing, right? But we can change this direction by just changing how these switches operate, like this. So if you took the same circuit and you switched the switches, right? Where, remember, this one used to be S1. Now we're going to make it S2. And this switch used to follow S2, but now we're going to make it follow like S1. So S1 over here, and this is now S1. So these two are now simultaneous. They're dual switches. And now these two are the duals. Okay? So all you did was just change these two around right there. And so now what happens when the two S1s are closed, which is that one and that one, this is what happens. So you have voltage right here accumulating this direction. The current flow is now going that direction because positive charge is going this direction under here. And negative charge is going this direction, but the negative current flow is the same thing as positive going the other direction, right? So current is going this direction that way. And then you open up these two switches here, and then you just have these two S2s. Those are closed, and now this just discharges. So now you have the same potential across here. So now you have no charge accumulated on here, and it just discharges. So for this momentary state right here, that holds its charge, but whenever it's closed, charge goes this direction, right? So it's going to the right, and remember the last one's going to the left. So you could change the direction that the current is flowing by just changing the polarity of your switches, S1, S2, and deciding which ones are the S1 and S2. Okay. Questions about that? Okay. Another thing you could do is this, which is really nice. So remember, this was our band pass that we went over in our review, right? We can replace both of these resistors by these switching capacitors, right? So here's our R2. It's going to be replaced by by this. Yeah, and in the picture, it looks like this is bigger than that, but in reality, this is much bigger than this. Okay, and we're going to place the Thevenin equivalent right here with this piece right here. Okay, and remember what these were. Here's the amplitude as a function of frequency. Right here. Here's the cutoff frequency, right, in terms of the R's and the C's. Here's the quality factor in terms of the R's and C's, right here. And here's what the band pass looks like at different, like a family of Q's, right here. So one thing we could do is this. We already know from our analysis that when we have these switched capacitors, we can just say, well, this R is the same thing as saying this T over this capacitor right here. In this case, is C4. And the resistance right here is just going to be replaced with our sampling period over C3, which is this capacitor right here. Okay, so that means that we could take these equations and just replace, the R Thev and R2 with these two things right here. And if we do that, this cutoff frequency now looks like this. Okay, and you can see the period here, sampling frequency right there, and here's the quality factor. Now, what's really nice about this is that we can change the resistance, right? You could change the effective resistance by changing this, and that only changes the frequency. So this is like frequency scaling, right? Without changing Q. Q remains the same. But this will change right there. So, so that just means that if you look at this plot right here, for any particular Q you're looking for, like let's say you're looking for Q4, the shape of this will remain the same, but the position, like this is the cutoff frequency right here, that position can shift. You can have it a higher frequency or sweep it low, but still hold on to the same shape for Q, for the fall off. Okay. Okay, and of course you could do the same thing with other ones too. So that was the band pass. You could do the same thing with the low pass. You could replace the resistors with the switch circuits, the switch capacitors, and same with the high pass, replace the resistors with the switching capacitors. Okay, and then of course these things would change. The R1 and R2, they would become the T over C, T over C, T over C here, same here, T over C's and all of those. And then you can change frequencies and other things. So it's a really nice way to have control over your filtering, right? So moving on to digital to analog conversion. Okay, so so they're written like this. D to A like that are DAC. So this is the interface between discrete digital signals and the real world, which is continuous. Okay, so you have your DAC right here, your digital to analog converter. You have some binary input into that, and you have your reference voltage, and then you have your output. Okay, so it's converting your digital input to some sort of like continuous analog signal coming out. And the resolution has to do with how many bits your conversion is. So if it's just voltage, you could do voltage or current, right? For voltage, you have this, your full scale voltage, right, multiplied by your bit signal. So you have your least significant bit and your most significant bit in this. And you also have some offset. And the offset is what you get when you have like no signal coming in, like no bits coming in. Whatever this is your offset voltage. And you may want to zero that out. But these bits right here are just ones and zeros because it's binary. Same thing with the current. Here's your full scale current right here. And these full scale values for the full scale voltage and full scale current, they're like multiplied by some value, like for example K, like whatever your voltage reference is, it could be amplified by some value K. Wherever your reference, wherever your reference current is, that V reference is going to be multiplied by some factor G to get your full scale current. Here are some typical values the book gave for the full scale voltage, like 2.5 volts, all the way up to like 10.24 volts. I guess those are pretty popular. And for the full scale current, it can range from like from 2 milliamps to 50 milliamps. Those are typical values for that. Okay, so the smallest voltage change for these digital to analog converters, that's due to least significant bit, this BN right here. So, so the resolution of your converter is going to be here. So your voltage of your least significant bit is going to be 2 to the negative of whatever number of bits it is times your full scale voltage. Okay, and B1 is the most significant bit, which is 1/2 of your full scale voltage. And here's an example. So let's say you have like a 12-bit converter, right? And let's say your full scale voltage is at 10.24 volts. Then here's what your least significant bit is for your voltage, right? It's going to be 2 raised to the power of negative 12, which is just 1 over 2 to the 12th, multiplied by your full scale voltage, right? And so it can change. The smallest resolution of change is going to be 2.5 millivolts. Can't get smaller than that in the ideal case. Okay, so it's like these quantum changes. So so typically when people talk about the resolution of, for example, the 12 volt, they'll say you have 12-bit resolution, or they can say the resolution is like 0.25% of full scale, or they can say the resolution is 1 part in 4096. All those are equivalent. They all mean the same thing, but that's what you may hear people talk about. Okay, and that value for 1096 comes from this, which is 2 to the 12th power, 12 bits. And these DACs typically range from 6 bits, which is like 1 in 64, and 24 bits, which is 1 in 16.7 million, which is really fine resolution. There's also different kinds of errors you can have. So I'm just going to show you what they look like. So here's your digital to analog output voltage right here times your voltage full scale. Here's like the binary input right here. The ideal case is this one right here, the one with the dots and the squares. That's the one you really want. But because there's a difference in offset and also a difference in the amplification, you could get something that's slightly like this. Okay, so here's like one source of error right here. So yeah, both gain and offset errors can cause that. Another type of error is linearity errors, right? Where this straight line is the ideal case, and then sometimes, depending on, and you'll see this in a second when I show you different kind of DAC circuits. A lot of times these things can like shift a little bit depending on what those ratios are, where you have a shift in your gain between those things in our offset. A third kind is called the non-monotonic, okay, where it doesn't increase monotonically. So monotonically, what I mean by that is that as your input increases, your output should increase at the same rate. But here you have this slope, here you have a different slope, up there you have a different slope. So it keeps changing. So that's not like a monotonic increase. And so that can be a source of error as well. Okay, and a few DAC circuits that we're going to go through. So one is called the N-bit weighted resistor DAC. This is the simplest one. This right here, as you're pretty sure you guys all recognize right here, it's a summer, right? Where each one of these is like an inverter right here, but it's summing all of these. And so what's happening is that here's your input stream, your bits from B1 to your least significant bit right here, and that just switches back and forth to let the circuit know which input you're receiving. And then each one of these, you have this resistor right here is 2R, that resistor is 4R to 2NR. And so even though that's like really simple, the problem with this one is that all these resistors right here, you have so many different values of these resistors, right? And it's hard to get them all right. And remember, this voltage that's coming through is going to be magnified by negative this feedback divided by that, right? So if these aren't all really exact, you're going to have things being added up that's going to be, it could be quite problematic, especially like if you have like a large value and it has a slight little change, and that slight little change is actually larger than your least significant change, right? You know, that could happen. Like the slight little error in here can pretty much, you know, dominate over the size of this error right there. So that's one right there. Another is this is the R to R2 ladder for this, and this is a little easier to deal with because you only have two types of resistors, R and 2R. So that's much easier to deal with versus going from 2R to this large value of R. That's a huge range to try to get right. These two are like maybe they're pretty moderate values. You'll have a better chance of getting these right. Okay. Another type is this type right here, which is the inverted R to R2 ladder. And you can see how it's inverted right here. The nice thing about this is that it doesn't suffer from the problems of this one, where This one has these reference currents, right? This one is always tied to ground, right? And this is tied to a virtual ground, right? Because if it's ideal, that ground is that ground. So you do have better performance with this type right here. But of course, you can always convert these things to just switches like this. Here's a invertedly monotonic DAC right here. And you could use switching capacitors like this, right? Where you just have capacitor circuits doing your switching. So in both these cases, this right here is very similar to the weighted capacitor DAC, right? Like if these were resistors. And this one is like the C2 DAC, like the latter one. So they're very similar, except you're just using capacitors instead of resistors. Okay. All right, so any questions about these things right here? All right, great. All right, that's all for today. I'll see you guys on Wednesday.